When it comes to delivering VR, an important use case to consider is streaming. Mobile HMDs, such as the Oculus Quest, are proving very popular. But for these to achieve their ergonomic requirements, such as being lightweight with a long battery life, they must compromise on computational power. Consequently, applications must either reduce complexity or offload it. This trade-off is nothing new, as render streaming, sending images rendered remotely, is receiving considerable attention as a solution to this problem. In our paper, though, we consider an alternative. My name is Sebastian, and I am from the Virtual Environments and Computer Graphics Group in the Department of Computer Science at University College London. And our paper evaluated how methods such as those applied to cluster rendering could be used to support streamed VR in an edge computing context. The motivation of our work was mainly curiosity, to understand the implications of streaming at different extremes. For example, which clients allow high-quality gaming over the public internet but have very high computational load. Render or video streaming has found a number of applications. It has significant challenges in VR, however, due to latency. Low-level streaming of geometry, commands, or transforms, such as that found in cluster rendering, used to be supported by dedicated physical networks. For mobile HMDs, we ask, what is their capacity to act as rendering nodes on high-quality wireless networks such as those found in edge computing configurations? Edge computing is a bit of a buzzword nowadays, but what it means is quite simple. It is an arrangement in which you connect two processors by a link of sufficient quality such that the larger processor can respond faster remotely than the smaller processor can respond locally. If the power differences are too small or the link is too low quality, then the whole arrangement becomes self-defeating. But if it works, you can get a considerable transparent performance boost. A second motivation for our work is the power characteristics of these smaller local processors. A mobile HMD is not simply a pared-down desktop. The challenge of small form factor electronics means that you can get quite distinct power profiles. Mobile GPUs, for example, are becoming quite powerful through architectures distinct from their desktop counterparts, for example, making use of tile-based rendering. Heat dissipation is a major factor for mobile chips, and this is what limits how fast CPUs can run. This puts an emphasis on dedicated co-processors and high parallelism, with each individual core having a fairly low speed. It is not then that tasks are hard for mobile platforms, but that highly serialized tasks will sooner hit the power wall of these devices. So, if we had a high-quality link, could we use what the mobile HMD is good at, i.e. rendering, to provide a low-latency experience where the critical loops are local while offloading the stuff it's bad at, i.e. physics? To evaluate this, we implemented a straightforward scene graph streaming application. Content was shared ahead of time, the host sent transforms, while the client sent user interactions. And our protocol also had support for different forms of prediction. We then ran a number of quantitative measures across the network with simulated degradation. Performance-wise, we optimized for latency and showed that our software could achieve relatively high performance, but that latency was higher than might be expected. The bulk of the delay is in buffering and is representative of what you'd find if you tried to build a real application. The important takeaway is that these latencies become high once frame quantization is introduced, and over a wireless link there is less capacity for synchronizing them. This will hold over any consumer-grade implementation, as though technologies like 5G promise 1 millisecond latency, this is only for the physical layer. Our baseline was run on a wired network to get the best performance we could, and that was still 15 milliseconds or so overall. To evaluate the error in what the user sees, we used clock synchronization to allow us to compare the rendered trajectories to a ground truth. Our results show that the distribution of errors is very skewed. The apparatus works perfectly 99% of the time, but the other 1% of the time it introduces severe errors. We classified the error into two types relating to spatial and temporal inconsistencies. That is, whether objects follow the remote server's trajectory but just delayed, or whether they deviate from it in space. Intuitively, temporal errors would be less noticeable so long as they are consistent between all objects. The user experiences the environment with respect to real-world time, however, so it is not as simple as A is okay and B is bad. Similarly, while spatial errors were more prevalent with predictors due to prediction error, these errors can be introduced without them due to quantization of curves. And finally, we looked at the predictors themselves. Simple per-object predictors are used in a number of applications, such as head and hand tracking. But for this application, we didn't find much evidence to justify their use. Overall, the time periods over which they would work are those for which the temporal delay would not be noticeable, and beyond this, you're in rich client territory. In summary, there is good reason to think that applying methods like cluster rendering in an edge computing context could work. The primary advantages are that they keep the critical loop local and make best use of computational power. The characteristics of this use case, though, mean we can't just naively use traditional methods. In future work, we need to much better understand how different types of inconsistencies affect the user experience, so that we can find low-cost ways of compensating for them on mobile platforms.